Welcome to our MOOC, or Massively Online Open Course, on Basic Steps in Magnetic Resonance. Today we shall be talking about chemical exchange. That is the subject of Chapter 4 of Peter Hoare's book. The author has chosen an example of chemical exchange for the title page of his book, so it is safe to assume that he found this subject particularly interesting. Like many other basic aspects of magnetic resonance, the effects of chemical exchange were discovered in the 1950s. The name of Herb Gutowski is often associated with discovery. The theory was initially developed by Felix Bloch and Harden McConnell. As we shall see, chemical reactions that occur during the observation of NMR spectra lead to characteristic effects: line broadening, coalescence, and line narrowing, all of which allow us to determine the rates of reactions. Typically, one can study rates that are comparable with differences in chemical shifts. The range of applications is truly staggering, from simple conformational equilibria to internal mobility of biomolecules, such as proteins. So, the word chemical exchange has a particular meaning for NMR spectroscopists, which is perhaps not shared by the entire community of chemists. To explain this point, let's consider some simple examples. All of us in first-year chemistry must have learned that cyclohexane normally looks like this if it is drawn as a static molecule, and that we have protons, or generally speaking substituents, sticking out from this ring in axial position, and other ones that are in sort of equatorial positions. Now we also know that this can interchange to give another chair conformation, which we can draw like this, which again has an axial and an equatorial position. Now what is curious is that in the static molecule, if we could stop it from exchanging, we would expect a different chemical shift for this axial position here and this equatorial position. One would expect them to have different chemical shifts. Let's not talk about the fact that they are also coupled. That is not currently of interest. Now it turns out that this position of the axial proton will be transformed, the chemical shift rather of the axial proton will be transformed into the chemical shift of an equatorial proton, whereas this equatorial proton will find itself in a position of an axial proton, and consequently there is an interchange between their chemical shifts. It turns out that this process is extremely fast and therefore difficult to measure with NMR, unless we find some way of slowing it down, which is actually rather still a topic of interest. I can take another example. This is more of a chemical reaction. Let's consider some carboxylic acid, which looks like this in the acid form, and we have all learned that this can be transformed into the conjugate base by losing a proton, or giving a proton to the environment. Now, if we think of the carbon-13 in this site, which we find on this side as well, we can expect the chemical shift of this carbon to be different from the chemical shift in the conjugate base. And indeed it is. Again, such a process tends to be very fast and therefore not easy to measure and appreciate with NMR, but it turns out that similar processes can be slowed down considerably. For example, if this carboxylic acid is hidden in the heart of a protein, belongs to the side chain of a protein, of one of the amino acids in the protein, in such circumstances the exchange can be slowed down and can actually become measurable, of great interest to NMR spectroscopy. Now, in order to support this whole discussion of chemical exchange, I invite you to look at Chapter 4 of Peter Hoare's book on nuclear magnetic resonance. You will see that he distinguishes symmetrical two-side exchange and unsymmetrical two-side exchange. We shall see in a few minutes what the difference is. And in this chapter there is a great wealth of very interesting examples that I will take some time to discuss with you. Let's first talk about symmetrical exchange, which I wrote here as exchange with equal populations. Equal populations you will have if the two forms in equilibrium have the same energy. So if the energy as a function of the degree of freedom turns out to have the same energy in the A and B forms. If that is so, then the populations will be equal according to Boltzmann's law, and also the interconversion from A into B will be precisely matched by the reverse interconversion from B into A. Such systems are very numerous, but we have an example here of dimethyl nitrosamine, where we have two distinct groups here, a methyl group here which is in a same side as the oxygen, or cis if you prefer, and another methyl group here which is on the opposite side, or trans, with respect to the oxygen. And as you can see, when there is a pseudo-rotation around this bond, this single bond, or partly single bond, then the oxygen will swap and go to the other side. And what was here, the methyl that was in the cis position now ends up in the trans position and therefore can be labeled like this. So the point is that while this pseudo-rotation is going on, the methyl groups change their environment, and so in doing so change their chemical shifts. Because the energies of these two conformers or rotamers are exactly the same, the populations are the same, and therefore we have a symmetrical situation where the forward and backward exchange rates are exactly the same, or we could write this as K plus is equal to K minus, or we can also write that the equilibrium constant in this case is equal to 1. Now, in this particular case, where we have equal populations, we can distinguish different regimes. And this picture you can also find on the title page of Peter Hoare's book. First of all, it shows the spectra that we see for such cases as a function of the exchange rate. And you will note that this is a logarithmic scale. For example, this corresponds to 1 jump per second, and this corresponds to 1,000 jumps per second. And of course, we go all the way to 100,000. This corresponds, generally speaking, to an increasing temperature. There are other ways, of course, of changing or affecting the speed of a chemical reaction, but temperature is certainly one way of doing that. And so at low temperature we have slow rates, and at slow rates we can actually distinguish the chemical shifts of site A and site B, as we have in the previous examples. In this case, at least in these simulations, they happen to be separated by a difference in chemical shifts, which the author tells us is 50 Hertz, and which elsewhere he calls delta nu, written like this with a lowercase delta. So that's the abstract notation for the difference in chemical shift, or if you prefer, we could say delta nu is equal to nu 0 of site B minus nu 0 of site A. Now, what is interesting is that if we increase the temperature or increase the interchange rate, then we see that the lines begin to broaden. And more surprisingly, they tend to move closer together. It turns out that the distance between this and this broad hump is smaller than the distance between the two narrow peaks at low temperature. And you see they get broadened to the point that we see almost no signal, and then they turn up as a single hump. The two lines are merged together into a single hump, a phenomenon that we call coalescence in our trade. And then, more remarkably, this single line, which is initially rather broad, will become narrower and narrower as the exchange rate increases, while at the same time we end up with an average chemical shift, which is simply halfway between the two chemical shifts of the separate sites. So at the low temperature end of our picture, we see line broadening effects which are due to slow exchange. Before we speak of line broadening, we have to define what exactly we mean by the width of a line. There are actually several definitions in the literature, but this is the one that we shall use. First of all, we consider the height of the line, just the peak height, and we call that uppercase H, and we divide that in two, and we measure the width in hertz at the half the height of the line. Now, this quantity we call delta nu. Nu is our Greek letter that we use for frequencies, and it can be shown that the line width is simply proportional to the exchange rate k divided by the factor pi. Since the exchange rate k is nothing else but the inverse of the lifetime of a particular conformer or molecular form, we can substitute that into this equation and come to the conclusion that the line width delta nu is equal to 1 over pi times tau, tau being the lifetime. Now, the width can be rationalized in terms of the lifetime of the states. Remember that a transition in NMR is always between a ground state and an excited state, but we have at the beginning of our book discussed these as stationary states that have an infinite lifetime. In fact, if the molecule doesn't exist for very long, the states don't exist very long either, and they get blurred. And the shorter the lifetime, or the faster the exchange, the more severe the blurring. And you can see that on the left-hand side they're only slightly blurred, and therefore the line is fairly narrow. But in this case the blurring is quite severe, and of course the differences in energy is also blurred, and therefore the line becomes very broad. So this is a hand-waving way of explaining line broadening. There are, of course, more satisfactory ways of explaining the same thing. So for a two-site problem with equal populations and equal forward and backward reaction rates, we have the following three distinct regimes. In the slow exchange regime, we simply have a line broadening which is the same for both A and B resonances, and in both cases is simply proportional to the exchange rate k, or if you prefer, inversely proportional to the lifetime of either of these molecules or conformers. In the fast exchange rate, we have an entirely different situation. In this case, the line width here is inversely proportional to the exchange rate. That means that the faster the exchange rate, the narrower the line. Furthermore, there is a very important parameter here. This delta nu is the difference in chemical shifts, so we wrote that as before, 0A minus nu 0B, that's the difference in chemical shifts, and as you can see, it comes here as the square. Now that's very important because that means that the residual line width here will be proportional to the square of the difference in chemical shifts. And this difference in chemical shifts is, among other things, proportional to the magnetic field into which we immerse our sample or a molecule. And consequently, if we go from, say, a 400 megahertz spectrometer to an 800 megahertz spectrometer, that is to say, if we double the field, then we also double the difference in chemical shifts, and we therefore quadruple the square, that is to say, the line width becomes 4 times broader. This is one reason why chemists and physical chemists like to have spectrometers of different fields in their laboratory. You can also convert this equation by saying that the line width here, apart from the square of the difference in chemical shifts, is directly proportional to the lifetime of the states. And then we mentioned that halfway between the two, there is a critical condition called coalescence. In fact, that's the precise point where the three extrema of these funny curves merge into a single extremum, a single maximum, and it turns out that that occurs when the exchange rate is precisely 2.2 times the difference in chemical shifts. Now this equation is of limited usefulness because in that vicinity of coalescence the lines are often so broad that you can barely see them, let alone decide whether they have been merged or not quite yet. We have just discussed chemical exchange between two sites that have equal populations because they have equal energies. But the discussion can be broadened to encompass the more general case where the populations are unequal. So here we have a case where we have on the one hand the same NNO residue, we have the same methyl group, but here we have replaced one of the methyl groups by a benzyl group, which is CH2 attached to a phenyl ring. And so these are clearly unequal, and therefore you would expect the molecule to have different energies depending on whether the oxygen is pointing on the same side as the methyl or on the opposite side. And indeed, the energies are quite different between these two forms. And therefore, the populations are going to be different. So there will be more molecules in this lower energy state than in the upper energy state. And we can also say that the likelihood that we move from left to right is faster, the exchange rate is higher than in the other way around. So this situation now means that KAB is different from KAB. This will have some consequences on the spectra. So when the populations are unequal, this has, as you might expect, dramatic consequences on the exchanging spectra. So here we have a case where the minor isomer A has about half the concentration of the major isomer B, but they still have distinct chemical shifts. In this case, the simulations refer to a difference of 50 Hertz. So this is again the delta, which is nu 0A minus nu 0B. And as you can see, when the exchange process begins to be felt, then the minor isomer broadens actually more or faster than the major isomer. Furthermore, they tend to coalesce and then narrow, as in the case before, but the narrowed line is not positioned halfway between the two chemical shifts, but displaced towards the major isomer. In fact, the rule is very simple. The average chemical shift is a weighted linear combination, or a weighted average, between the two chemical shifts, with the population of the minor isomer and the population of the major isomer, which are applied as weights to these two chemical shifts. Remember that the sum of the two populations is defined to be 1, because these are probabilities of occupation. As you can also imagine, if the major isomer becomes very dominant, the minor isomer becomes negligible, and the average line will be essentially indistinguishable with the position of the major isomer, and that becomes therefore difficult to determine exchange effects. It turns out that this picture is quite a modern picture. I guess it was first drawn in the 50s, but there has been recent work going on in proteins where one can now distinguish the dominant major conformation of a protein and a minor conformation which might be activated, perhaps the conformation that allows the protein to work as an enzyme or have a fruitful interaction with its substrate. And this kind of argument is now used not only for protons but also for nitrogen-15 and carbon-13 in proteins, and turns out to be a very powerful way to identify mobility of macromolecules. Now, if the populations are unequal as opposed to the equal case we treated before, then, as I said, there are two different line broadening effects. The line width of site A becomes inversely proportional to the lifetime of A, and the lifetime of site B is inversely proportional to the lifetime of site B. If site B is dominant, then its lifetime will be longer, and therefore its line width smaller. If this is a minor conformer, then tau A will be short, and therefore its width larger. Furthermore, we have this average population, which, as I said, is weighted by the populations, and this is a somewhat more scary equation where we have the residual line width in the high temperature limit, in the fast exchange limit. And here we see that, much like in the case of a symmetrical exchange, it is still proportional to the square of the difference in chemical shifts, and therefore if we double the field, this delta nu parameter will be multiplied by a factor 4 like before. Furthermore, we see that we have PA and PB, these are the populations, and the sum of the two exchange rates, the forward and the backward exchange rate. Of course, this should converge with a simple equation if we take PA and PB to be 1/2 each. To summarize the first part of Chapter 4, we have discussed the pictures that serve as front cover for Peter Hall's book, and we have discussed the fact that if there are two isomers or two molecular forms or two partners in a chemical reaction that have different chemical shifts, then these lines will be broadened by the chemical exchange, and the broadening can go as far as coalescence and beyond into a line narrowing at an average position. And the line widths of these different spectra can be used to extract the chemical exchange rates, which of course are of great interest to chemists and physical chemists alike.